found this exotic pattern of 2 spins up, 2 down, 2 up, 2 down, and so on. So it's not the canonical up, down, but 2 up, 2 down. So we refer to them as blocks. So that was a big surprise. So this is an example where the computer discovers a state that you were not expecting. So that was quite interesting. And then the itinerant electrons, because of the Hund coupling, so each one of these represents 3 orbitals, but all this happens at the same site. There is a Hund at coupling, to follow the Hund rule of physics. So the mobile electrons tend to follow the orientation of the spin of the localized degree of freedom. Okay, so we discovered that. And then Jacek Herbrich, who is full of energy, decided to start changing the electronic density. The one I showed you before was at a very particular electronic density, but he managed a clever way to simplify the problem from 3 orbitals to 2 orbitals. You cannot go all the way to 1 orbital because then you miss the whole thing. But as long as you have 2, you can still be fine. So he found a clever way to do it. And consequently, in this OSMP, you have 1 degree of freedom that is localized, almost localized, and another one that is itinerant. And he and collaborators, they changed the electronic density and found a variety of other unexpected states. For example, at a particular density, they found these blocks, 3 up, 3 down, or 4 up, 4 down. But the area in parameter space was getting smaller and smaller. So probably there is a 5.5, 6.6, 20.20, I don't know, but certainly on regions of parameter space that are shrinking in size. And then to the other side also there are exotic states. They are signaled by a peak in the static structure factor, S of Q. So the evidence is pretty overwhelming that you have all these states. They are all emerging. By the way, don't pay too much attention to whatever is below these purple lines. This is for a senior scientist to remember all the million parameters that we have. So yeah, if someone asks me about some parameters, there is 0 chance that I will remember the numbers. So I have written them here. But so this is only for me. Apparently, the DMRC was done on a chain of 72 sites. This was also done in ladders. In ladders also, you have these unexpected states emerging. Each one of these lines that you see are legs of the ladder. In this case, you have in the run, contrary to the copper ladders that some of you with some seniority may remember, contrary to the copper ladders, in this case, the rungs are ferromagnetic. And then sometimes you have blocks 2 by 2, as in the case I mentioned before, which was the one confirmed experimentally. And here you have these 2 materials are real materials, and experiments have been done with neutron scattering, and these magnetic orders have been confirmed. So others have not yet, but apparently it's difficult to get single crystals for these materials. But you have all these exotic states that you find only because you have good tools to do the calculation. Then we made predictions for inelastic neutron scattering. My understanding is that the single crystals are not big enough for a good experiment, so the inelastic prediction remains to be fully confirmed. But what we found is results like this. By the way, this is a huge effort numerically because my collaborators who did the real work follow they target different values of the frequency. And here there are about 200 frequencies that they target. So it's like 200 times the DMRG effort. But it was done. The signal that you see here dominant is a spin wave with, because we have these blocks of two sides, we have the Goldstone mode is at pi/2 in the canonical notation, because you have double the size of the magnetic cell. And also there are other levels that we refer to as optical modes. At finite energy, they seem to be very flat, suggesting that they are localized. And we have analyzed their behavior, and they seem to be excitations of the blocks, internal to the blocks. So these arrows, they seem to be so rigid and well-formed. Actually, you see that we're working at a value of the Hubbard U equal to the bandwidth. So that's more or less the beginning of a strong correlation. So these are not rigid structures. And the Hund coupling is a quarter in units of U. It's not infinite. So you can have excitations where instead of the maximum spin, you have less of that. So there are internal excitations within the block. This is for the case of 3 up, 3 down. And now the spin wave has the Goldstone mode at pi/3. And there are also optical modes. And there are also signals, this, experimentally, this has not been seen yet, or the experimentalists didn't pay too much attention, but there is a prediction that there should be some weight at pi as well, because this, the separating the 3 up and 3 down, there is a sharp wall. This is not a cosine or a sine modulation, but a rigid boundary. So when you Fourier decompose this, all modes are there, and pi happen to have a good weight. So this is highly non-trivial. Well, these youngsters that surround me keep on working. The results that I show you were for U/W equal to 1. So the previous page was along this horizontal line, and we went through blocks 2, blocks 3. There is a tiny space for block 4, and so on. But you can change also the value of the interaction U. You can go deeper into strong coupling and so on, or to weak coupling. And they found this phase diagram that contains all kind of block states shown in green here. There are all kind of little boundaries separating the many blocks. It's not presented in the illustration. There is, of course, a paramagnetic area early on. Then we found some ferromagnetism. This is a common feature when you dope a multi-orbital system. The physics of so-called double exchange kicks in. Sometimes it's convenient to align all these localized spins to facilitate the movement of the mobile electrons. And then we also found this mysterious green island where the peaks in S of Q were incommensurate, and they were moving as we were traveling, say, along the yellow region, the positions were moving. And in the original paper, we just refer to them as incommensurate phase without much more detail. But then the effort continued, and we discovered that these type of incommensurate features were created by spirals. Spirals that were of a novel variety. A regular spiral is as shown at the top. You have a tilting angle. I mean, the spiral can be oriented, with the spins perpendicular to the main axis or along the main axis. There are a variety of ways in which you can do it. But here there is all the spins are perpendicular to the main axis of the chain, and there is a tilting angle, which is the same from one spin to the next and to the next. But what we found is that because we're so close to these blocks, the spirals were made out of individual blocks. So you have two spins up, then there is a tilted angle separating these two from another two, and then from another two, and so on. So we got a a block spiral. That is, to my knowledge, that was the first time observed. So it was published here in the Proceedings of the National Academy. There is one material where diffraction neutron scattering, not the inelastic. The elastic neutron scattering shows incommensurability, but they don't have single crystals. The effort more or less stopped at that point. And this is, notice that, I didn't tell you with precision what Hamiltonian I was using. I was using the Hubbard model multi-orbital, but there is no spin-orbit coupling included explicitly. There is no frustration in the sense of interactions at long distances, yet we have this type of spirals. But if you look at the phase diagram, now you see that there is some sort of competition. There is a region which is ferromagnetic, very prominent. In the extremes, there is anti-ferromagnetic order, like in here, up, down, up, down. So there is a sort of pressure from the left and the right for the spins to try to accommodate and keep happy the dominant voices left and right. So there is a sort of hidden frustration because there are competing tendencies. Super exchange is up, down. Double exchange is the one that generates the up ferromagnetic order. So it's, from that perspective, once you see an enlarged phase diagram, then you start rationalizing why in 2014 we found this block kind of state. We refer to that as hidden frustration. We should have a more sexy name for that. Okay, so here comes the most recent and exotic portion of the presentation, when the Majoranas make it into the game. So what we did in this publication was it's a big effort. So we placed the spiral using a chain of 36 sides. We placed that on top of a plane where we put BCS standard superconductivity by hand. So we added an attraction by hand and used the so-called Bogoliubov-Deschênes equations to handle that. Is a very standard procedure. And the size of the plane that we use is this one here. It was not a square, it was a rectangle. And we coupled the two, allowing for particles to move from one to the other. So the goal that we had was to induce superconductivity into the spiral. So this is an area of research that is in the area of Majoranas is very much used. The so-called proximity effect, superconductivity. Once you have some tendencies that would allow to create triplet superconductivity. If you have a background that is a spiral-like, the singlets are not the only channel in which the pairing can go, the triplet as well, and the triplet is the fertile environment where the Majoranas develop. So we did a self-consistent calculation, and we allow only for pairs to jump back and forth. The C and A operators are both fermionic. The C corresponds to the chain, the A corresponds to the plane, so they jump in pairs. The overall number of particles is conserved. And we use a self-consistent approximation to handle that. So it is exact within the chain and self-consistent with respect to the movement back and forth and the actual plane. So that was the technicality. It was a big effort. And these are the very exciting results. First of all, this is the density of states at the chain. The one at the plane is more or less canonical, is a BCS superconductor. But at the chain, we induce a gap, which is what we wanted. We wanted to induce a superconducting gap. Here we have the length of our meager 36 sites. Sorry, we cannot do much better. So we induce a gap. But these peaks are the interesting result. So these peaks are Majorana states at zero energy. And if you calculate expectation values, you will see that in this regime, there is in the chain an induced singlet and also an induced triplet pairing. Both of them are induced there, as it has to happen for a topological superconductor. So it's I think that the reason why the publication appeared in this prestigious journal is primarily because we are removing assumptions that people made before. There are people that are, let me jump. I will talk about this illustration in a few seconds, but let me say for fairness that there were publications before with similar ideas, but employing frozen classical spirals. But we have removed that assumption by working with quantum spirals that are generated spontaneously in some region of parameter space, in this yellow portion of parameter space. And what is interesting is that although you can access the yellow region in many directions, a nice way to sell the story is that you fix the density and you are increasing the Hubbard U, and then you go first through the collinear block portion. That could be up, down, or two up, two down. So this is what happens here. You don't have any Majorana. You have a gap induced by the proximity effect, superconducting gap, in the green region. And then as you keep on increasing the Hubbard U, and you penetrate into the spiral region, in the spiral region, the density of states will have a feature at energy zero, which are these Majoranas that are living at the edges. So that was quite interesting. Now, if you pay attention to the numbers are huge. So these gaps are huge. If you happen to translate that into the analog in temperature, these are hundreds of, probably close to 1,000 degree TC superconductors. We had to exaggerate the numbers, and the referees understood that clearly. The reason is that these Majoranas have a size that depends on the gap. And we have the restriction of working with a finite size chain. So if we can reduce the gap, there is no problem. The trouble is that these yellow wave functions start overlapping. And eventually they overlap so much that it's a bit difficult to tell them apart. So you have to, it is allowed in theory to exaggerate in order to capture the essence of the problem. So this is what we did. Okay, so there are other manners. This is a side comment. If you are too tired right now, you can take a 2 minutes break. This is a side comment. There are other ways in which we have worked generating Majoranas, and you can consult these publications. The leader of the calculation was Mohanta, who is now back in India. This is not DMRG. This is primarily it's a Monte Carlo simulation in many respects, but of the easy variety. For example, we have 3 layers essentially. There are more in the structure, but essentially you have a layer at the bottom, which is this complicated skyrmionic crystal. So this is the analog of the spiral that I showed you before. Then in the center you have an electron gas. The electron gas will be the one that is suffering the influence of the bottom, the skyrmion crystal, and the top. The top happens to be a superconductor. The green region is a superconductor. In principle, you could have a difference in phase between the two regions, but in practice, we just took zero difference. And then we carve a channel which somewhat resembles the 1D chain, but it's similar but not identical. So this 1D channel has superconductivity nearby from the top, and this generalized spiral arrangement of spins, skyrmions, at the bottom, and we found that it also generates Majoranas. This is not the true local density of a state. This is just, of course, a little triangle from PowerPoint. But if you were to check the presentation, the paper, you will see the peaks in the density of states. So there are a variety of ways in which these things can be done. There are other groups that have worked with a similar geometry. They didn't carve this 1D channel, but they observed that Majoranas sometimes appear at the borders. So that's another area that we are trying to get our hands into. And other groups are ahead of us, the possibility of Majoranas traveling at the border. Okay, and we are arriving now to work in progress, or that was recently submitted. These are moving Majoranas, meaning we want to have a procedure in order to translate, to move these Majoranas at a speed that we can regulate. So the models that I showed you before, Hubbard, multi-orbital, with a Hund coupling, with all kind of subtleties, those are for now too difficult to handle, because what we are doing here is a time-dependent problem. What I showed you before were time-independent. They had the omega dependence, but things were static. But here we will have a real time. So what we did is we took the 1D Kitaev model. This is the model that can be solved exactly. I remember some time ago I reproduced the paper of Kitaev. It took me like 10 pages of algebra, but indeed this model can be solved exactly, and indeed it has Majoranas at the edges of a chain with open boundary conditions. And that model is the hopping, the superconducting term, and some chemical potential to regulate the density. Note that there is no spin index in the creation operators and destruction. There is no spin index because these are spinless, which is the same as saying they're all pointing the same way. So the superconductivity that you are creating here is a triplet superconductivity, which is the one that is the nicest for these Majoranas. But in addition, we added, to be a bit more realistic, we added some repulsion between electrons to see what sort of effect it caused. There are only a few groups that have studied the Kitaev chain with repulsion. So these are the motivations for doing this work. And here, what I just unveiled is an area that I know next to nothing, is the famous braiding of Mayoranas. Turns out that these Majoranas are so popular these days because they could potentially be used as qubits in quantum computing. It's a dream. I don't know whether I will see this during my lifetime, but the fact is that in order to carry out operations and act as a quantum computer, you have to do a movement of Majoranas called braiding. So, for example, here you have 4 Majoranas at the initial time, and you have to move them around each other in clever ways in order that the outcome mimics operations that you want to do in a computer. The AND operation, the OR operation, and so on. So you achieve them by moving the Majoranas. This is non-abelian physics. You will get matrices involved. It's very complicated, and I barely know what I'm talking about here. I'm just repeating what I heard. The fact is that you have to learn how to move these Majoranas. But there are a few problems. If you try to move the Majoranas too fast, then they become they essentially become deformed. So this is extracted from the book of Griffith in Introduction to Quantum Mechanics. If you have, for example, the ground state of the infinite square well, which is a sine function between 0 and a, and you can expand this wall into 2a. You can do it very slowly, and they refer to that as an adiabatic process. And you can keep the shape. The energy is not conserved when you do that, but you can keep the shape. So this sort of sine or cosine looking form remains. Now, you can do it abruptly, like if it were two containers, one empty and one full of water, and then you remove the wall in between. You can imagine that there will be a wave of water going from the left to the right, hitting the boundary, and continue oscillating. And if energy is conserved, because for an abrupt movement, energy is conserved, so this will be a mess. As time evolves, you will see a wave that comes back and forth, and it just never will produce a stationary state. So you don't want the thing to go too fast, because you get this issue. But also you cannot go too slow, because if it goes too slow, there are decoherence processes that are acting like phonons that destroy. In principle, the Majoranas are supposed to be very robust, but given enough time, the decoherence will occur. So there is a window in time where these things could happen. So this is what we did in a paper that was recently submitted. So the spikes in green are the Majoranas. This one is moving to the left. It started at the place that I'm marking here. And then what we did is, side by side, we increased the potential at each of the sides. So at first, at one extreme, sort of slowly, we move the potential towards a large number. That forced the Majorana to jump to the next side. We repeated the operation, each jump to the next side, and so on and so forth. And there is a number called tau. It's a time that regulates the movement. We have some, if you check the publication that hopefully will be in the archive soon, you will see some numbers in nanoseconds and so on, but I don't want to give too much importance to that. This is a toy model only. But the fact is that this is what essentially happens. You have the local density of states on a chain of 12 sites that you solve exactly. You do the dynamics of that. You do all these gates, movements, and then you can translate that from 12 to 6 without any problem. And between 6 and 12, you have a potential that is so large that there are no electrons. Here in the inset, you have the electronic density. Between size 7 to 12, there is nothing, because you have moved the potential very high. And then all the electrons are in this part of the problem, right? So this is an adiabatic motion. We did it. If you do it too fast, then this Majorana gets all deformed, and there are all kind of wavy things, as I mentioned before. There is another operation that is quite interesting to do, and we have done it, which is you can continue with this Majorana going all the way toward the position of the other one, right? So eventually the two will collide. It is expected that when two Majoranas are put one on top of each other, there are two channels in which they can react. They can annihilate each other, or they can merge into a full electron. There are two channels. Essentially, it's like having a symmetric and antisymmetric combination of the Majoranas. I forget which one gives what, but although there is barely any overlap, there is a tiny tail of each one of the wave functions. So you can, like any pair of localized wave functions at a final distance, there is a symmetric and antisymmetric combination. So that creates a tiny separation in energy. When you focus on one of them, you go into the annihilation and you get a hole. And when you go into the other one, you get the electron. And these are the local density of states at site 1, the very first one, after the fusion has occurred. And under some circumstances, the only thing that survives is the blue, which if you have amazing eyes, you will see that it says electron, and the hole, there is nothing. If you choose the other of the two channels, symmetric or antisymmetric, then it's the opposite. They annihilate. Well, you get the opposite result. So there are no electrons after the fusion in one case, and then there is a full electron. One means a full electron after the fusion in the other channel. So we're working on this. Someday, in an optimistic perspective, someday we will have larger geometries that allow for the exchange of these two. For example, if we go into a ladder geometry, or we have some other geometry, for example, a Y juncture, you can exchange them, and you can test the properties of their non-abelian nature. George, I have used 45 minutes, so I don't know what to do right now because I'm about to reach the last point. Obviously, I have been talking very fast.
I think you can go ahead.
Okay. No problem. This is a good moment to ask the audience if they have any particular question, because what I will jump into now is related, but is not so smoothly related. You have seen a continuity from page to page so far. This will be a little bit of a detour. So if there is any question, this is a good moment to formulate.
Okay, I'm checking here. No one raised his or her hand. So I think you can go ahead.
Okay, no problem. Okay, so this is the last topic. And this is now adding yet one more complication to the mix, which is the possibility of superconductivity, but not the one of the variety that you put by hand, like in that geometry where I had a spiral chain on top of a BCS superconductor. This is immersion superconductivity we're talking about. So because this is the story. Probably for the young people, they don't know how the different fashions evolve in physics. So until recently, there were like two camps that were marching very strongly each, but with little communication. One was the issue of topology. The issue of topology was primarily driven by band structures, non-interacting electrons, and the presence of a spin-orbit coupling. So under those circumstances, you get all this interesting physics of Berry phases, of Chern numbers. You have all these topological concepts. And then you had the correlation school of thinking where, for instance, the cuprates had correlation effects inducing superconductivity and all kind of orbital order, the manganites, the nickelates. But now the people are starting to study the two together. Like, by the way, this spiral that I mentioned in that yellow phase, that's an example where you're mixing things. You're mixing topology, the Majoranas, and the correlation, because the phase appears only when you have a robust correlation. There is another axis, unfortunately. So it's like the story never ends. So you also have the doping, that in many cases is crucial for it to go superconducting in the family of the copper oxides or the iron superconductors. You need to dope the system. You have to, typically it's hole doping, but electron doping also leads to superconductivity. You either remove or add extra carriers. So someday we have to mix everything, we have to put everything together, topology, correlation, and doping. So it's going to be a big challenge. So eventually, showing that the story never ends, we have a three-dimensional space that we eventually will have to cover. One axis is the Hubbard U, that by itself is a super challenge. Then topology, if you work along this axis that's 0U, then you can do a lot of topology, usually with the addition of a spin-orbit coupling. Now, if you mix topology and correlation, and you are somewhere here, well, that's the result I show you of the spiral and the Majoranas and all that. Now, in principle, there is also this axis, which is the doping. For this, the high TC superconductors are living here. The spin-orbit coupling doesn't play a role in the correlated superconductivity, but the correlation does and the doping does. So eventually we have to visit what kind of entities are in the middle of this humongous space. We barely have touched this area. So what I will show you are modest first steps in that direction. And what we are doing is we took the Halden chain, which contains some, it was the first baby steps that opened the gates into the frenzy of topology. We will dope it. This is something that Haldane didn't do. And Ian Affleck, another of the leaders in those days, they didn't do. We will dope it. And we found that numerically that it goes superconducting. So what I will show you is just a summary. You can consult this publication. So I'm giving you just a few words of a big effort. The fact is that we managed to construct a variational state for the two-orbital Hubbard model. The two-orbital Hubbard model, if the hoppings of the two orbitals are similar or equal, the two orbitals at every side, because of the Hund coupling, they will form a spin 1. So in other words, in a chain of spins 1, once you model that using two orbitals, you can think of these little green spheres as a spin 1/2. At orbital A, there is another spin 1/2 at orbital B, and the Hund coupling will favor the combination of a spin 1. So at large U, what we study in this paper becomes the Halden chain. So what we discover, this part is very cute, and I think it merits extra work. So we did the writing of the spin 1 in terms of the spins 1/2. This was also done by Affleck a long time ago, but he was just using artificial spins 1/2. Here we're using real degrees of freedom, the orbital degree of freedom. But then the spins 1 that we generate at every side, we couple them in a global spin 0 singlet. So it's not just up-down, but it's up-down minus down-up, but in the language of a spins 1, which is more complicated than just what I just said. So we have a singlet of spins 1. And we discovered by doing this analytically that they are made of spin 1/2 singlets. So there are like preformed spin 1/2 singlets hidden in the physics of a spin 1 chain. So this is a variational state that you will have to accept my word for now, but apparently it captures the essence of the problem. We have done calculations with the variational state and compared with Langshaw's, and it works very nicely. There is a large overlap, good agreement for spin correlation, and so on. So believe it or not, this is a way to think of the spin 1 Haldane chain. You have two orbitals, A and B, And the rule to construct the variational state is at the beginning you pick up one of the two. This is an edge. You pick, for example, orbital B, and you select a neighbor, either one or the other, and form a singlet with that neighbor. This arrow, this blue arrow, denotes a canonical spin 1/2 singlet. And by construction, this remains spin 1. This is how we started. Then the rule says that once one of these spins is coupled in a singlet, the other one has to pick up a partner. For example, here is the same orbital again. And you continue the same way. There is always an unpaired spin 1/2 in search of a partner. In this case, it goes among different orbitals. So it goes between B and A. And then you continue. And then you have to make all the possible combinations with equal weight. So it resembles a state that perhaps in recent times is not as much mentioned as it was in the past, the resonant valence bond of Phil Anderson. It was essentially a state for high TC superconductivity made out of spin 1/2 singlets. But here this is surprising because at the end of the day we have spins 1. So who could have imagined that a bunch of arrows that are double the length of a spin 1/2, a spin 1, and you may think that they will go up, down, up, down, up, down, they have this amazing internal structure. So this is what we are discovering. In principle, it is in agreement with the original ideas of Haldane, but put in a much more eye-catching and intuitive manner. Also, we see the edge states, because when you start the process, there is a spin 1/2 that is alone. And when you end, there is another spin 1/2 alone, these are features that were considered surprising in the physics of the Haldane state. So from here, in the last page, I promise this is the last page, then goes the notion that superconductivity could be possible, and indeed numerically this is what we found. And the story links the copper ladders of the 90s, where I was very much involved in, and the new way of looking at the Haldane system. So in the good old days, this is a true ladder. So each one is a true different copper atom. So this is leg 2, leg 1. It was discovered in those days that if you wanted the most simplistic perspective of the order of spins, you could not say, I will place a spin 1/2 here, up, down, then up, down, and so on. You have to link them in singlets because it has a spin gap. Otherwise, you cannot generate a spin gap. So you need to place them in a singlet, up, down, minus, down, up, and then a singlet at every single run. So that is more complicated than a bunch of little arrows, but that is the proper way to represent a spin system with a spin gap. So now you dope. Every time you dope, you are removing one electron, and you are breaking one of these nice singlets. So intuitive, this is very crude, but it's a cartoonish explanation that seems to work. Every time you introduce a hole, you are breaking one of these singlets. When you have another hole, you break two singlets. The damage to that background of singlets is minimized if you put the two holes together. This naive, simplistic view was tested numerically extensively, and it seems to work, and also experimentally. Now we go into the new entity. So now this is the new proposed variational state for the Halden chain, but looks like a ladder, but is actually a chain. But it looks like a ladder because I'm separating the orbital A from the orbital B. So there is something deep that we didn't have time to penetrate into, but legs of a spin 1/2 with only one orbital are pretty much equivalent as orbitals just a chain, not a ladder. And I try to convince you that we have preformed spins 1/2 singlets. So same story. You add a hole, you break a spin 1/2 singlet that was very happily formed. You add another hole, you break another one. The way to minimize the damage is to put them together. And in this publication, you can see the numerical evidence that this thing is working. Experimentally, it's going to be difficult because you need two orbitals that are degenerate, and these crystals have the tendency of always deform, create a lattice distortion, and break the degeneracy. So I'm told that this will be difficult to create experimentally, but anyway, that's the prediction. So in summary, the Halden chain represented as a two-orbital Hubbard model with a unit matrix so far is predicted to go superconducting with hole doping. The signal is very robust. And one of my collaborators is working on trying to relax that story of using the unit matrix hopping and see, after all, the dominant singlet appears to be diagonal. So we will see how adding extra hoppings, mixing the orbitals, how the superconductivity is affected. Anyway, I understand that this part was complicated, and I apologize for that. But this modern physics is complicated. Okay, well, so this is a summary. You can read it yourself. These 4 items are basically the same as in the introduction. And these are the main references, the same that I mentioned along the way. Okay, thank you very much.
Thank you, Elbio, for this very nice talk, very didactic and very interesting. So we are open to questions now. Does anyone have a question? See here, I do have a couple of questions if nobody jumps in right away. We did Q-rate superconductivity long time ago. One of the messages I got from working on that field was that spin fluctuations could lead to hole pairing. What are the consequences for superconductivity of these block magnetic states?
Good point. We tried that, George. It didn't work. So turns out that let me find this. What George is saying is that after all, this is a glorified way of going antiferromagnetic. If instead of up down, you go two up, two down. But there is an antiferromagnetic order, which it simply involves a different wavelength. So you may be tempted to think that you could dope, for example, one block with a hole and another block with another hole, and they may prefer to be close to one another. But apparently that was too optimistic, because the holes, what they find out, these holes, is that energetically for them, the simplest thing to do is to start like resonating inside the block. It's like the kinetic energy of jumping from one to the other. I'm trying to do that with a mouse here. That kinetic energy dominates, and so it's a long story, but the short message is that we try to look for binding of two holes in this type of environment, and we found nothing.
Okay,
it just didn't work.
But this material, the 123, the barium, iron, selenium, is it superconductor?
Oh yes, this one goes superconducting at high pressure. So it is true. It's paradoxical. We have not found it so far in what we do. Believe me that we look for it, But so yeah, we have this. So what the people doing density functional theory tell me is that with pressure there are also deformations of the lattice that may play a role. Also, there is a possibility that we may jump. Let me give you the other state. Remember that we not only have the 2x2 block, but we have this one.
Okay.
This one, yes, this one goes superconducting in the computer. Oops, in the computer as well. So these blocks do not seem to be the most fertile area for pairing, but this one is okay. So this is what we have found. So the speculation in some publications of other people is that they started with our work and then they added pressure. Is that as you increase the pressure, you go from the 2x2 into this one. You metallize the system and then superconduct. So it's a bit complicated, the story, George. Sorry.
Okay, no problem.
I can refer to the papers I'm talking about.
Okay, no problem.
Just a quick question about this figure. This kind of the spin that you see different structure there, right? Did you check only numerical, or do you have any idea why you have this kind of partners of this spin there?
So why we have this type of orders?
Yeah.
So that's the question. Well, let me, if I understood correctly, the question is the way to rationalize why we have this type of orders, which are exotic, is to go into an extended parameter space and see what are the competing tendencies. We know that there is a ferro, there is an antiferro standard, and then in principle you could jump through a first order phase transition between the two. That's fine, but sometimes the system chooses to find intermediate states. So you can look at the two block. The two block has inside the block ferro, in between the blocks antiferro. So it's partially keeping happy the ferro tendency, partially keeping happy the antiferro tendency. So we think it's a compromise. This is why you understand this type of states only when you see the entire phase diagram. And we have done this also with Hartree-Fock in 2 dimensions. It's the same result. You get in the area between two big dominant forces, you get all kind of complicated states. Not only these ones, you get many others.
I wonder if the Y-way interaction would explain this kind of structure that you see. RKI interaction.
Oh yeah, that's another possibility. Is I have not pursued that line. I know that others have pursued that line. The RKKY is an oscillatory interaction, but
the density.
It could be. It's just that because we are dealing with values of the couplings that are robust, we at least myself, I tend to think of RKKY more of a weak coupling approach. So I am not saying that is wrong. It could be. I am not excluding that idea at all. It's just that apparently these blocks go all the way to such a large value of U that you start doubting on the validity of RKKY. But look, in summary, my answer is this very well could be understood also within RKKY. So it's a compromise.
So before Aaron asks the question, Gineton has asked to, he has raised his hand. So Gineton, please ask your question.
All right. Thank you for the nice talk. My question is on a spiral that you place it on the top of the superconductor. So my question is the following. So is there an advantage of using spirals over the traditional, for instance, rush-by-wire proposals for the Majoranas, or there is nothing you compare when you compare these spirals of the superconductor and the rush-by-wires?
There is not much of a debate, and now that you're asking that, that reminds me that I didn't say a word of what I myself wrote here, which is, turns out that once you have a spiral, in this case in the C operators, you can introduce a rotation at each one of the sides. You can redefine a new fermionic operator, multiplying the C operator by a phase factor, e to the I some angle, so that in the new fermionic system, you have a ferromagnetic kind of chain, because you are rotating every side. But in doing that, you also generate extra terms. So so because it depends on the side, every side has a, you rotate in the proper way. They call it a gauge transformation. And then it has been shown by other people, by the people that I cited, I will put the citations next. It has been shown that if you have a chain with a Rashba spin-orbit recoupling, a uniform magnetic field, and the proximity of superconductivity can be gauge transformed. This is a mathematical operation that I have done it myself. Believe me, it's not too difficult. It is transformed into the new fermions, into a spiral arrangement of the fermions as opposed to a ferro system, plus the superconductivity that is untouched. So I think these are just two ways to see the same effect. So you can transform one into the other. So you can say that this spirals actually is Rashba physics hidden after a gauge transformation.
Okay. All right. Thank you.
Yes, that was another long answer.
Oh, okay. Aaron has a question.
Yes. Thank you for the nice talk, and George for organizing this. I have two questions about the moving Majoranas. The first question is, I didn't understand what causes the movement of the Majorana. And the other question is, what happens if one Majorana meet another one during their movements?
Okay. How do we move them?
Okay.
What is expected to be done experimentally, and what we did in our theoretical study, is we move them by hand. So what we did is, say, in the Kitaev chain, remember that we have a superconducting gap at the center, and so these two things are placed at the edge because it's the only location where they can be. So there is this correspondence between the bulk and the edge. So they are there because that's the only place. But if we slowly increase the potential, first at where I am with the pointer, then in the next side, then in the next side, essentially we are reducing the length of the Kitaev chain. We are not doing it by killing sides, but simply by raising so much the energy there, the potential there, that electrons don't want to be there. The number of electrons in the red region is basically zero because we are moving the potential so high. So essentially we are reducing the length of the chain, and we do it via the experimentalists do it with so-called gates with just electric potentials, right? So this is not that the Majorana wants to move. It's just that we are kicking and pushing the Majorana with a wall that we are moving towards, in this case, towards the left. So we are moving them by hand.
You are squeezing the chain.
Yeah, exactly. So if we have a long chain, we are making it shorter, and the Majoranas are always at the edge of the chain. If we do it slowly, if you do it very fast, the poor Majorana gets confused. But yeah, we are squeezing them. Yes,
Okay.
that's a good way to say it. And the other question was about the fusion. You were saying?
Yes. Are them protected from themselves, the Majoranas? What happens?
No, they are not protected. So they have this channel, these symbols, this is not a true multiplication and a true sum. It's in the sense of decays. And so when we bring two Majoranas, each one represented as a gamma here, and when you put them together, the channels of decay are into a hole or an electron. So when you place one on top of each other, you no longer have two Majoranas. The concept of Majorana is gone. You either have a hole or you have an electron. Basically with equal chance, 50-50. Because the Majoranas, if you look, we have done it. When I say we, that means some of my young collaborators have done the composition of in the local density of states, what portion is electronic-like and what portion is hole-like, and they found it's 50-50.
Oh.
So the Majorana is a mixture of equal weight of an electron and a hole, but when you put them one on top of each other, they can decay either into a full hole or a full electron. And there is a number that my recollection is that it's called the parity. So these Majoranas, or a finite chain, they seem to be totally independent of each other, but they are not. After all, you cannot kill one without killing the other. These things are connected at a distance. They are entangled at the distance. So, and they are entangled in any finite system in a symmetric and antisymmetric manner. So although we don't see it very clear that energetically we are talking about minuscule numbers, there are two states, the symmetric and antisymmetric combination, or parity 1 and parity -1. And depending on which of the two you are, you will end up in the hole or you will end up in the electron as a resulting consequence of the merging. So, yeah, it's quite fascinating. And but there are things that we don't understand. For example, look at this one. This is time. Essentially, you can relate this to the sides. So 0 here means the Majorana you are moving is at the far right. Then you keep on going that way. That means this Majorana is moving this way. You have an electronic density that, well, is not exactly 1/2, because here we have the potential that is also causing some disturbance, but very close to 1/2. It is moving that way. And then when the two get close to one another, not on top of each other, we have this anomaly that we don't understand. First, it looks like you will create a hole, and then you go into the electron, as opposed to a smooth race into the electron or a smooth decay into the hole. So these oscillations, we don't have a clear understanding. Because really, when you are at side 10, well, pardon me, when you 10 counting from the extreme going to the left, so basically when you are next to each other, it looks like you will create a hole, but then you create an electron when it is truly on top of each other. So there are a few things that we still don't understand.
Yes. Thank you.
Okay.
Elbio, just a question related to that. This non-charge conservation originates with the fact that you have a superconductor nearby, right? Because let's say you started in this chain, you started with 12 electrons, and then you created the Majoranas, and then you join them together, and it can go either way, either one way or the other. Mm-hmm. So you would end up, if you have a hole, then you would end up with 11 electrons. So yeah, this one electron that is missing was lost to the superconductor.
In short, yes. Okay. Now, note, I should have said this and I forgot. Note that I'm focusing here on omega 0. So the true density of states is you have a gap, that is the superconducting gap, that is supposed to go through everything, but it's a topological superconductor, or in this case, it's a full 100% triplet superconductor. So there are a bunch of electrons, there could be a bunch of electrons above, but there are none, but below the gap, there are plenty. So, because I'm focusing on omega 0, you only see the activity at that energy 0, but there is plenty of other electrons in the system regulated by the chemical potential. So, you are, in essence, what you said is correct. Yes.
Okay.
You're coupled to a superconductor. Charge is conserved overall because you have this bath of electrons in the condensate. You have the luxury of decaying into a hole or decaying into an electron. But there is a background that takes care of the global conservation laws. Yes.
Okay.
It's subtle. These things are very subtle and very interesting.
Yeah. Could be that there is this dip and this little jump that you were mentioning that is under a reflection or something like that?
Could, at this point, I say yes, could be, because I have no clue what it is. So could be anything. Frankly, could be anything.
That's a good point. Yeah, that's a good point.
It is to be decided. But this is strange. It seems to be collapsing into a hole. Because, look, historically, to be totally frank with you, a priori, we didn't have a clear understanding of which of the two parities will give which of the two channels. So, but we had them under good control, the parity plus and the parity minus. Sometimes, depending on the way you order the fermions, the plus and minus are switched. So we said we have the two channels. Each one is supposed to decay one way or the other.
Okay.
Right. And indeed, we found that. Now, that's part of the issue, that we have to go all the way to the initial state that we are selecting to try to decipher from what is causing this stuff. So I'm saying in a variety of ways that I have no clue.
Okay. I would have one or two more questions if nobody else is raising his or her hand. One of them is on that very nice diagram that you showed of topology, correlations, and doping. In the topology and correlations, it's I may have a naive understanding of correlations, but if correlations are very strong, I lose the band structure language, right?
That is true. So one
And
thing
I
that
understand,
could,
yeah.
one thing that could have happened, George, is that these two things could never cooperate. They would just compete.
Okay.
So I was expecting, and I think it's still to be expected, that in many cases that are topological and weak coupling, as you increase the value of U over W, you lose the topology into some garden variety, into some interesting but non-topological correlated state. That may easily happen.
Okay.
Now, our case is a counterexample, because after all, the way we are selling this story is that, you see, in order to get the Majoranas, you need the spirals. And in order to get the spirals, you cannot just stay in weak coupling, which I'm trying to show here with the mouse. You have to penetrate some distance into the correlation axis.
Okay.
So at least in this example, I don't know how genetic it is. This is what we did. Who knows how many stories, how many ways to reach the same answer people can have. But in our case, you need the correlation in order to create this non-trivial Majorana physics.
Okay. Okay.
Now, I wouldn't be surprised if in other cases, the beautiful churn numbers and these currents that are supposed to be non-dissipative, that they are totally killed as you increase the U. I wouldn't be surprised.
Okay. Well, in this case, in this specific case you mentioned that there is a mathematical way of showing that there is an equivalence between the two, right? That there is this gauge transformation that...
Well, it's an equivalence between introducing the equivalence is between having a spiral state, which is crucial in order to have this mixture singlet triplet, or having a Rashba type and uniform magnetic field. I mean, there is a mathematical equivalence between those two.
Okay.
That's not an equivalence between correlation and topology. It's,
No, exactly. It's just two different ways of getting to the same place.
In the same place, in the sense of the Majorana, yes.
Or the Majorana, yeah, but not the. I see no way of defining Chern numbers when you put correlation. You go to Fock space, you don't use band structure anymore. How are you gonna do the Berry connection and everything?
The only thing I know, and I have not done it myself, although I should, is they look at this anomalous quantum Hall. They look at, right. So if you have access to sigma xy in the correlated system, we can imagine we know how to calculate, for example, the optical conductivity, the sigma xx, and you can do it at omega 0 or at finite omega. If you go on sigma xy, you focus on omega 0, you are supposed to have a quantum anomalous effect. So if the sigma xy at omega 0 is non-zero, the number that is multiplying the unit of conductance, the E square over H, the integer that is multiplying is the Chern number.
Okay.
There is a paper by my collaborator, Maria Dagotto. Well, I don't have the picture of her, but this is the last name to follow.
Okay.
So Maria Dagotto has a paper many years ago, actually, at least 7 or 8 years ago, using Lanchos. She and collaborators calculated precisely the anomalous Hall effect for an interacting system and has a story about the Chern numbers in a correlated system. So.
But is that number expected to be an integer?
Good question. Good question. You're exhausting my knowledge here.
Okay. Yeah.
I think from my recollection of what Maria said, it just happened to be because to the extent that you associate the Chern number to the number of channels of conductance at the boundary,
it should be an integer.
It should be an integer, right?
Okay.
As a matter of fact, what we have done, nothing to do with the talk, but we have started with two-dimensional system non-interacting with the conditions to generate a Chern number. And then we started reducing one direction, the length of one direction, not contracting all the way to a chain, but going to a small size ladder, let's say. And we basically see that the number of modes don't change at all. The way to calculate the Chern number gives you a non-integer. So there is something wrong in the way in which people canonically calculate the Chern number through those integrals. You remember that there are these integrals of derivatives of this and that in momentum space. If you do it that way, you don't get an integer. But if you count the number of modes and the number of Dirac cones, you get an integer even when you shrink one direction going into a more rectangular ladder-like geometry. So there are plenty of things that people have not investigated. So.
Well, Gineton has a question.
Yeah, I have just one quick question, but I think it's more a technical question because you are considering a chain of 36, right? The length of the chain. And I was wondering because there's one paper by Miles and White. It's also on the DMRG approach, and of course, it's not in a spiral, but it is the Rashba wire, and they are claiming that when you go to smaller size of the chains, you can barely see this topological phase where you can see the Majoranas. I have tried to reproduce some of his results, also using the DMRG approach, but using a different language to see the signal of the Majorana, which was using tracking the Majorana correlation. And so far, I could not see signal for lengths for the chain when it's like smaller than 120 atoms. But of course, there is this difference, right? With you're using this spiral language, and also you're using superconductor, which is in a plane. So the way they do it, and the way that I tried also to reproduce, we just put this superconductor pairing, right, by hand.
Yeah.
This S wave. So I was wondering if you not have any overlap already in this 36 when you have this short length of chain.
Well, it's a bit difficult a question because it refers to work done by others, and I need to see the details. If you could send me the reference, I can comment on some on my perspective on the topic. But yeah, it's. I'm sorry, without penetrating a bit deeper into the publication that you cited, I don't have much to say.
Yeah, because the length you're using, the 36, right? It's usually smaller than you usually see in the literature for these Rashba wires. So as you said that you can compare both of them by a mathematical transformation. So I was wondering how could you see this even for this smaller chain?
Oh, you mean how can I see this?
Yeah, because like paper of White, he has to go for 400 sites.
Well, probably it's because they have not exaggerated. Here, remember that we went brutal in the size of the gap. This is a gigantic gap. Okay, it doesn't seem too impressive as a 0.2 electron volt, but if you translate that into degrees, it's a gigantic number. This is not a typical gap of a superconductor. So perhaps an answer to your question and is that to the extent that you want to remain realistic in the values of the superconductivity that you are using to induce the pairing, to induce the topological superconductor, if you, to the extent that you remain realistic, certainly 36 will not work. You will need a few hundred sites. So that's for sure.
Okay.
So by the way, I still would love to see the paper if you can send that to me by email or just the reference.
Sure.
But for example, let me go into here. Mohanta, who is a more realistic individual that wants to always be in contact with real numbers. This is why he has to do all Bogoliubo the Chain and the price you pay to be realistic is that you have to lower the quality of the many body techniques that you employ. Narayan Mohanta typically uses much more realistic numbers. You can find several papers of him, not only these ones. And indeed, because the gaps are much smaller, if you are realistic, the chain length has to be much larger. I totally agree with that. If this is what you were the message that you were trying to pass to me.
Yes.
But consult the papers of Mohanta, but he's using Bogoliubo the Chain. So it's a superconductivity in the singlet and triplet channels with realistic numbers, very small gaps, that means realistic superconducting gaps. And he has to use large chains in order to see the physics of the Majoranas. Otherwise, they overlap so much that you see nothing.
Okay, I see. All right, thank you.
Okay. But send me the reference. I would appreciate reading that.
Sure. Thank you.
Well, if we don't have more questions, I don't have any more. I already asked many, so thank you again, Elbio. Very nice talk.
Right.
Oh, there is a question here, a last minute question.
Last minute question.
Lauro, go ahead, please.
Oops.
In reality, Lauro is a student with Luis Diaz. He is in Sweden now, working with Annika Blackschaffer.
Okay.
Where is Lauro? He's having technical problems with the microphone, I guess. Lauro, are you there? Yeah, there he is.
Can you hear me now?
Yes.
Oh, nice. All right. Thank you for your talk, and nice to meet you, Elbio. My question is regarding the last part of your talk, specifically about the superconducting state you're showing to us. I just would like to know if it is already now which kind of symmetry the gap function of those triplet states can present.
Let's see.
In order to identify which kind of superconductivity we could observe in those states.
Well, the question is well formulated, but remember that this is a chain. So if we are talking about symmetries in a one-dimensional system, you either have a singlet or triplet with regards to the spin. So I'm assuming that the only symmetries that matter is reflection symmetry in 1D. So these are spin singlets. There is not much more that I can say right now. Let me see. This is 1D. That's the problem. This is not like a 2D system where you can make an elaborate rationale on whether you go D wave, S wave, etc. This is just 1D. So I think the maximum I can say is that this is the singlet channel. But perhaps there is a symmetry that I'm missing related with reflection. If there is a symmetry that I mix related with reflection left-right, sorry, but I don't know the answer. Maybe there is a parity plus or minus also, but if there is such a thing, I haven't studied yet. But you know, at least you see, all this has a long history, and originally people that work along this line, because of the fact that we have a triplet, we have these spin ones pre-formed. It was assumed that probably this would be triplet superconductivity. And I think with Jose Xavier, we have papers along that line. We have a PRL, 1 or 2 PRLs along that line. So originally it was assumed that, and we found that this triplet superconductivity. If you consult this paper, there is a huge area of the parameter space where the superconductivity is a triplet superconductivity, not a single. But there is a region where it is singlet. So I am not answering your question properly, my apologies, but for the time being, we have been focusing on singlet versus triplet, and the only other quantum number I could imagine in 1D is the reflection symmetry, the parity right to left, and there is nothing else.
Yeah, I'm asking that because I already had a conversation with one of my professors that some people do say that actually we could try to think about collective states in terms of symmetries, but others say that actually correlations are more relevant in order to talk about those stuff. That's why I'm asking about symmetries. But in this case, correlations are relevant, right?
Well, probably what you are implying is a notion that many people are discussing in the context of a spin liquids, because after all, this is a spin liquid. In the context of a spin liquid, where you don't have through any robust long-range tendency, people are talking about the entanglement within the spins in the spin liquid as the order parameter. You know, it's the degree of entanglement. So maybe this is what your professors are trying to tell you, but I don't know. I mean, you can also write to me with more specific statements on what you would like to discuss. But yeah, in many cases in correlated systems, you have different channels regulated by symmetry, and you choose one or the other. The moment you lose the long-range order, then you have to resort to other more subtle ways that usually go along the line of how much entangled your bunch of spins is. So it's complicated, yeah.
Yeah. Thank you very much, Elbio. Nice to meet you.
No problem, and send me a question by email with some reference or something.
Okay, Elbio, I assume that you are tired already. You have been talking for almost 2 hours straight. I have to apologize.
Sure.
Say that again.
I have a correction to what you said. I have been talking almost 2 hours straight here, but remember that I was lecturing for an hour and a half until 15 minutes before the starting time.
Yeah, so you are probably very tired, so it's time to let you go. Just to matter of full disclosure here, I made a mistake because for technical reasons, I took over the ownership of this room, this virtual room, from Edson, my colleague. Because he was at a conference, so he wouldn't be able to open the room, so he passed the ownership to me. but I forgot to check that I could turn on the recording device. So once you started, I tried to put to record, but then I had to call him on Skype and ask him, please come in and turn on the. So long story short, we are missing the first 5 minutes maybe of your talk. So if you want to pass that to someone, I will give you the link later. And I will ask for the slides to put together with the video in our YouTube channel. And then if you pass the link to someone, warn them that the first 5 minutes, the first 2 slides are missing. I apologize for that. It was my fault.
That's okay. But for example, could you like me? Look, my technical knowledge is very limited, but at least within PowerPoint, I know how to operate the recording portion of PowerPoint.
Yeah, no, this is.
I didn't know how to merge that with the other one. So if you want me to record myself, and you tell me how many pages, I can do it. If it is 3 or 4 pages, it can be transmitted by the internet.
Let me see.
The first 20 minutes in my laptop.
Oh, okay. So okay, great. So we have that covered, because then we can put the 2 videos together, and whoever wants to watch everything, just jump from one video to another, and it will have the whole thing. Okay, great, Xavier. That was good. Yeah. So I was saved by my colleague.
I didn't know I was being recorded. Good thing I didn't make any politically incorrect joke or something.
Yeah, well, I should have asked you for, but when I saw that I couldn't record, I went in panic mode and called Edson, and then I forgot to tell you that we were recording. But
I'm on Latin America. It's more relaxed this time.
Yeah, it's more relaxed, and I don't recall any jokes, any improper jokes, let's say.
That's right. Now here is that thing is far more complex.
It's far more complex and dangerous, very dangerous.
And extremely dangerous. Yeah.
Yeah.
So, you have to ask for permission for everything. The issues of privacy are very problematic. So yeah. I don't know. Okay. Things are weird. Okay, exactly. So probably it's time to go, right?
Yeah, I thank you very much again. It was very nice interacting with you again, and I hope that with Lauro, the student who just asked you, he is a student of Luis Diaz. He is doing his master's with Luis Diaz. We are working on applying the RPA to the twisted double layer graphene, and we are floating the idea of doing the same for the nucleates, for the nucleates. And so we may send you a draft to take a look once we have it. But
okay, sure.
He's doing a great job, I must say, Lauro. He's learning the technique very fast and has already a code that is working. So we're going to start applying it to different systems.
That's very nice. These twisted systems, the only thing we have done so far is real space Hartree-Fock that doesn't take into account. I mean, it's a sophisticated Hartree-Fock because it's a long story, but it's more than the canonical Hartree-Fock. But it's still the quantum fluctuations are not there. So, so we are discovering all kind of exotic states, but we don't know how robust are against quantum fluctuations. So your contribution via the inclusion of the RPA would be great.
Yeah, there is some RPA done by the group of Tomali, I think, Ronnie Tomali from Dresden, if I am not mistaken. But AI space for more stuff, I am sure.
Of course. And also you have this dichalcogenize, not just graphene. There are these other materials.
Okay, yeah.
Gosh, I'm forgetting right now what is the advantage compared to the graphene. Darn it. Well, for some reason there is like among the theories there is a transition from the bilayers of graphene into the bilayers of this transition method dichalcogenize. And that is attracting a lot of attention. For example, Alan McDonald is working on the dichalcogenize much more than graphene now. So
okay,
but you could use the RPA. The point is that you could use the RPA there as well. Well, anyway.
Yeah. Okay, Xavier, do you want to mention anything?
A quick comment, Elbio. Do you remember that we studied the two-leg condor ladder?
Yeah, I remember that. Yeah.
We have some block structure like you saw, and you explain that using the RKKY there.
Oops. Okay. Oh, really? How embarrassing! My God.
It's
okay.
Very similar. And you explain the block structure with the RKKY. That just a comment. So it's nice to see you.
Thank you. Yeah, when you are close to 500 papers, you start forgetting your own papers, and there is some decoherence in the brain. But well, thank you, Jose. I will take a look at those papers. I will make sure to include them in references because they deserve to. If we have these block structures. Yeah, so probably I have rediscovered the same thing we discovered time ago. Wonderful. Okay, guys, it's a bit late, but
okay, very nice. I will send an email asking for the slides.
Okay. Bye, George. Bye, Jose. And if there is anybody else, so Lauro is supposed to send me something, and there is another one that
Gineton too.
Oh yes, that's right.
Yes.
Okay.
Okay.
Cheers. I will see you. Bye bye.
Good seeing you, Elbio.
Ô Jorge, está indo aí, Jorge?